Hello everyone, this is Afzalur Rahman. In our today's class, we are going to discuss about some of the important concepts of optical isomerism. So first of all, we will discuss about plane polarized light, that is PPL, plane polarized light. Okay. So what is plane polarized light? We know this ordinary light consists of some electromagnetic radiations. Electromagnetic radiations. Now what are these electromagnetic radiations? We know these electromagnetic radiations, they are generated due to the combined effect of electric and magnetic field. Electric and magnetic field, okay. And we know that this ordinary light contains some electromagnetic radiations or electromagnetic waves which vibrates in different direction. Okay. Suppose if we consider this one, suppose this is our ordinary light, okay. So it will vibrate in different directions. It will have vibration in different direction, okay. Now when this ordinary light is subjected to nickel prism, okay. Suppose we have here we have our nickel prism subjected to nickel prism, okay, and the light which is coming out from this nickel prism will have vibrations in only one plane. Here you see in this ordinary light it will have different vibration in different direction, okay now, but after subjecting to this nickel prism, the resultant light which is coming out from this nickel prism, okay now, it will have vibrations only in one plane. Such a light or such a beam of light, okay now, is called plane polarized light. Okay. So here we can have this type of vibration that is in one direction or single direction only, okay now, or they will vibrate in one plane. Okay. So such a light is called plane polarized light. Okay. Once again I am repeating, we know this ordinary light consists of some electromagnetic radiations, okay, and they vibrate in different directions in different plane, okay. And after subjecting this ordinary light through nickel prism, the resultant light which is coming out from this nickel prism is found to have the vibrations only in one plane. Such a light is called plane polarized light. Okay. Or this plane polarized light can be obtained by passing this ordinary light through nickel prism. This is nickel prism. This is ordinary light, and this is PPL, plane polarized light, okay. And these plane polarized lights, they are very much important for the determination of optical activity of many compounds, many organic and inorganic compounds, okay. So these are plane polarized light, okay. Now this plane polarized light, as I have mentioned here, these plane polarized lights are important for the determination of optical activity of many compounds, okay. So next we are going to discuss about optical activity, okay. Here we have optical activity. Now what is optical activity? There are various organic compounds, okay, which can rotate the plane polarized light, okay. So such substances which rotates the plane polarized light, they are called optically active substance. Okay, and the phenomenon is called optical activity. There are many organic compounds, for example glyceraldehyde, for example lactic acid, okay. So these molecules, they are optically active compounds, okay, and these optically active compounds, this can rotate the plane polarized light. And such substances are called optically active substance, and this phenomenon is called optical activity, okay. Now suppose if we consider this is the solution of any optically active compound or optically active molecule. This is the solution of any optically active molecule, okay. Now if we pass this plane polarized light, through this solution, okay, optically active compound, the solution of this optically active compound, we will find that this optically active compound can rotate this plane polarized light either in the right direction or in the left direction, means either in the clockwise direction or in the anti-clockwise direction, okay. Now if this compound rotates this plane polarized light, suppose this is PPL, plane polarized light, if this compound rotates this plane polarized light in the right direction, or you can say that if it rotates it in the right direction, okay, suppose this is plane polarized light in the right direction, then this is called dextrorotatory, okay, then it will be called as dextrorotatory, okay. Or if it rotates this plane polarized light in the left direction, suppose in this direction, in the left direction or anti-clockwise direction, here this is clockwise direction, okay na. If it rotates in the clockwise direction or right direction, then this will be called dextrorotatory. And if it rotates the plane polarized light in the left direction, or anti-clockwise direction, then this will be called as levorotatory. Okay na. This dextrorotatory comes from one Greek word, okay, dexter. This dexter means right. Dexter means right. Dextrorotatory. And this levorotatory means, this levorotatory is taken from one Greek word levus. Laevus. Levus means left. Okay. So now, if this compound, the solution of this compound can rotate the plane polarized light in the right direction or clockwise direction, then this will be called dextrorotatory. And if it rotates the plane polarized light in the left direction or anti-clockwise direction, then this will be called levorotatory. Okay. This dextrorotatory is represented by one symbol, that is, we can represent this dextrorotatory with d, small d, or with the help of one algebraic sign, that is plus or plus. Okay, to indicate this dextrorotatory, you can use small d, the symbol small d, or this algebraic sign plus, and this levorotatory can be represented with the algebraic sign, with the letter small l and algebraic sign minus. Okay, small d or small l. Small d means dextrorotatory, or it will be represented with plus. Small l means levorotatory, or it can be represented with minus. Okay. Now, if we consider one molecule, suppose glyceraldehyde. This glyceraldehyde is an optically active compound. Okay, means it will have plus isomer also and minus isomer also. Okay, so it will have two types of isomer, and this plus and minus, these isomers are called optically active isomers or optical isomers. They are called optical isomers. Okay. Suppose if we consider glyceraldehyde, this glyceraldehyde have both this plus isomer and minus isomer. Okay, and this plus and minus isomers, they are called optical isomers. Okay. Now, next we are going to discuss about asymmetric molecule. Okay. Now, what is asymmetric molecule? The name itself indicates here. Asymmetric molecule means the molecule which lacks all types of symmetry. Next is asymmetric molecule. Asymmetric molecules are those molecules which lacks all types of symmetry. Okay na? The molecules, you can write here, the molecules which lacks all types of symmetry. Okay na? Such molecules are called asymmetric molecules. Okay. Suppose if we consider one example, suppose if we consider carbon, we know the valency of this carbon is 4. Okay, and in these 4 valencies, if we put different types of atoms, okay, suppose at the first valency, suppose we have here A, here we have B, C, and here we have D. Okay na? So here you see at the 4 valencies we have different types of atoms. atoms, okay, and such type of molecule will lack all types of symmetry, means this type of molecule will not have any plane of symmetry, axis of symmetry, and point of symmetry. It will lack all types of symmetry, and such types of molecules are called asymmetric molecules. Such types of molecules are called asymmetric molecules. Suppose if you consider, if we replace this D with B, okay na, is this molecule is a asymmetric molecule? No, this molecule is a symmetric, because here this we have two similar type of atoms, okay, so it may have one plane of symmetry, it may have axis of symmetry, it may have some other types of symmetry also, okay. So this is not, this is, if here is B, then this is not a symmetric, this is a symmetric molecule. But here, if all the positions, all the groups are different, all the atoms are different, then such molecules are called asymmetric molecules. Then such molecules are called asymmetric molecules, okay. And this asymmetricity is very, very important for showing optical activity, for showing optical activity, okay. Remember, this asymmetricity is very much important for showing optical activity. If a molecule is symmetric, then it will not be optically active. It will not be optically active. Okay. To show optical activity, the molecule must be asymmetric. Okay. Next, we are going to discuss about chirality or chiral molecules. Next, we are going to discuss about chirality or chiral molecule. Okay. So next one is chirality. Now, what is chirality? Here you see, any object which forms a non-superimposable mirror image, they are called chiral. They are called chiral. Okay. Suppose if you consider this hand, okay, now this hand, the right hand, okay, now. So if we use one plane mirror here, okay, so we'll get the reflection of this hand in this direction, okay. So what will be the reflection? The reflection of this hand will be this left hand. The reflection of this right hand will be my left hand, okay na. Now if we put this right hand over this left hand, okay na, is it superimposable? No, okay na. So they are chiral. They are chiral, means any object which forms a non-superimposable mirror image. Now see, here you see, this is the mirror image. This is the mirror image of this one. This left hand is the mirror image of right hand, okay na. But if we superimpose, okay na, then they are non-superimposable. It has been found that they are non-superimposable, means any object which forms non-superimposable mirror image, they are called chiral. They are called chiral. Okay. Now, suppose if I consider this one, this paperweight, okay na. Now, if you use one plain mirror here, okay na, what I will get, okay na, I will get the same molecule, same here, okay na. Is this chiral? No, this is achiral. This is achiral, means they are this one and its mirror image both are similar. Both will be similar. So they are achiral. They are achiral. Okay. Okay, so but this hand, okay na, this hand is the example of this chiral. Okay, chiral means any object which forms non-superimposable mirror image, they are called chiral. They are called chiral. And the phenomenon of this showing this non-superimposability is called chirality. Is called chirality. Okay. Now next we are going to discuss about enantiomer. Next we are going to discuss about enantiomer, okay. Enantiomer, okay. So before coming to this enantiomer, let us take one example. Suppose if we consider here I am giving one example of this chiral molecule. Suppose if we consider carbon. Now if in this carbon, if we have CH3 in this first valency, here we have hydrogen, here we have chlorine, here we have Br, okay, bromine, okay. Now here you see this molecule, this carbon molecule is a chiral molecule. This carbon molecule is a chiral molecule. Why this is chiral? Because at the 4 valencies it contains 4 different atoms, and this molecule is an asymmetric molecule. This molecule is an asymmetric molecule, and this molecule is also a chiral molecule. Okay, now if the 4 valencies are different, now if we consider here mirror, if we consider the mirror here, okay, now what we will get? We will get the reflection here. Here you see CH3 bond C star. So after reflection, okay, here you will get Br here, okay na, and this hydrogen will be shifted to this side. So here you have hydrogen and chlorine here, okay. Now if we put this one over this image, okay na, what we will get? If we put this molecule over this molecule, what you will get? You will get non-superimposable mirror image, okay na. So this will not fit over this one, okay na. Here you see, if we put this one over this one, okay na. So this Br and hydrogen, here will have a hydrogen and Br. Okay, so will not match. It will not match means they are non-superimposable. They are non-superimposable means they are chiral. They are chiral. Okay, and here you see in this chiral molecule it contains one chiral atom, one chiral carbon. Okay, so this chiral carbons or this based on this chiral carbons, its optical isomers can be measured. Okay, so how these optical isomers can be measured? Here you see we have one formula 2 to the power n, 2 to the power n. Okay, now here you see in this molecule we have one chiral atom means 2 to the power n, 2 to the power n means 2, means this molecule will have two optical isomers. Two optical isomers, one may be plus and that may be minus. Okay, now if any molecule contains two chiral centers, so it will be 2 to the power 2 means 4. It will have 4 optical isomers. If any compound has 3 chiral centers, so it will have 8 optical isomers, like that. Okay, now so based on number of chiral atoms, chiral carbon atoms, 8 optical isomers can be measured. Okay, can be calculated. Okay, so now here we are going to discuss about enantiomer. Okay, enantiomer means any optical isomers which forms non-superimposable mirror image. Okay, now which forms non-superimposable mirror image, they are called enantiomer. They are called enantiomer. Suppose if we consider the example of glyceraldehyde. Okay, now if you consider the example of glyceraldehyde, the formula of glyceraldehyde is CHO, C, OH, H, and here we have CH2OH, CH2OH. Now here you see, is this carbon a chiral carbon? Yes, this carbon is a chiral carbon. Means this molecule will be an optically active molecule. Okay, now will be an optically active molecule. So it will have some other isomer. Okay, so if you use plain mirror here, what you will get? You will get CHO bond C star. Here we have OH, here we have H, and here we have CH2OH, CH2OH. Okay, so here you see they are optical isomers. Okay, and they are mirror image of one another. Okay, but they are non-superimposable. Means any optical isomer which forms a non-superimposable mirror image of each other is called enantiomer. Now if we put this one, this is over this molecule over this one. Okay, now will it match? Will it superimpose? No. Okay, now it will be non-superimposable. Means this OH part will be in this direction. Okay, now so here we have hydrogen, so it will not match. It will not superimposable. Okay, now superimpose. So any optical isomers which forms a non-superimposable mirror image, they are called enantiomer. Means these two are enantiomer. Okay, now these two are enantiomer. Okay. Now the next topic that we are going to discuss is diastereomer. And next one is diastereomer. So next topic is diastereomer. Okay, now so this diastereomer will discuss with the help of an example. Okay, now let us take the example of this 3 bromo 2-butanol. Okay, now let us consider this molecule. Okay, now so here we have CH3 bond C, or we will write with the help of bond line notation. Here we have OH, here we have H, here we have H, here we have Br, and here we have CH3. Here you see this is 3 bromo 2-butanol. 3 bromo. Here we have this carbon number 1, carbon number 2, carbon number 3, carbon number 4. So 3 bromo 2-butanol. This molecule. Now here you see in this molecule this carbon is chiral carbon. This carbon is also a chiral carbon. Okay. So it will have one optical isomer, or it will have one mirror image. So here you will get the mirror image here. Here we have CH3. Okay, and here we have CH3. Now after reflection, what we will get? This OH group, this is in the right side, but this will be reflected in the left side in this reflected part. So here we have OH, and this hydrogen will be shifted to this position. Here hydrogen, we have hydrogen first. Here we have hydrogen, and this Br will be shifted to this position. Okay, so suppose this is 1 and this one is 2. Okay, now let us consider another one. Suppose CH3 bond CH3. Okay, so here we have OH, here we have H, here we have Br, here we have hydrogen. Okay, so if this molecule will have another isomer, so what will be the isomer here? You see we have CH3 bond CH3, okay, and here we have OH, H, here we have Br, and here we have H. Okay, so here also these carbons are chiral carbon, this chiral carbon, this is chiral, this is chiral. Okay, now here you see, suppose this is molecule 3, this one is molecule number 4. Okay, so here you see, if we consider this one structure 1 and structure 2, okay, you see this is 3 bromo 2 butanol, this one is also 3 bromo 2 butanol. Now this molecule have the mirror image, this one, and these two molecules are enantiomer. Why they are enantiomer? Because they are non-superimposable mirror image, because they can form mirror image. But if you put this molecule over this molecule, okay na, so you will find it is non-superimposable. Okay, so that means this 1 and 2 they are enantiomer. Now if you consider 3 and 4, if you see 3 and 4, here you see these 3 and 4 also, they are also enantiomer, because they are non-superimposable mirror image. Okay, they can form mirror image, but they are non-superimposable. So means this structure 3 and structure 4, they are non-superimposable mirror image, means they are enantiomer. Now if you consider 1 and 3, structure 1 and 3, okay na. So here you see this structure 1, 3, they are neither superimposable nor they are mirror image. Neither superimposable nor they are mirror image of each other. Okay na. So they are called diastereomer. So this 1 and 3, they are neither mirror image nor they are superimposable. So they are diastereomer. Enantiomer means this 1 and 2, they are mirror image, but they are non-superimposable. Okay, and this diastereomer, they are neither superimposable nor they are mirror image. Okay na, so they are diastereomers. So this 1 and 3, they are diastereomer, and 2 and 4 also, this 2 and 4, they are also diastereomer. Okay, so these optical isomers which are neither mirror image nor superimposable, okay, they are called diastereomers. Okay, so the next topic, after that, the next topic is mesocompound. Okay, we know this chirality. Okay now, this chirality is very much important for a molecule to show optical activity. But it has been found that in some molecules, in spite of having these chiral carbon atoms, they are optically inactive. Okay now. So such type of molecules are called mesocompounds. Okay. So next one is mesocompound. So what are mesocompounds? There are such certain compounds in which, in spite of the presence of these chiral carbon atoms, they are optically inactive. And such molecules are called such compounds are called mesocompounds. Let us consider example of mesotartaric acid. Mesotartaric acid. Okay na? What is the structure of mesotartaric acid? The structure of mesotartaric acid is, here we have COOH, here we have COOH. Okay, so here we have OH, H, OH, H. Okay, so this molecule is chiral molecule. This one is also chiral. Okay na? So both these carbons are chiral carbon, but this molecule is optically inactive. Okay na? So why this is optically inactive? It contains chiral carbon atom. Besides this chiral carbon atom, it is optically inactive. Now question comes, why this is optically inactive? This compound is meso compound is optically inactive because of the presence of plane of symmetry. You see here in this molecule, okay na, this molecule will have plane of symmetry, means this molecule is not an asymmetric molecule. This is a symmetrical molecule, means the reflection of this upper part is the the lower part is the reflection of this upper part, or vice versa, okay na. So it has one plane of symmetry, plane of symmetry, and because of this plane of symmetry it is optically inactive, okay na. So in this molecule there is this compound is optically inactive because of this internal compensation, because of internal composition, means this upper part of this molecule will have one rotation. Suppose this upper part is dextrorotatory and this lower part will be liborotatory. This lower part will be liborotatory, okay na. So this upper part, this dextrorotation will be cancelled by this liborotation. By this liborotation, as a result, this compound will not show optical activity. This compound will not show any resultant optical activity, okay na. So because of this plane of symmetry, the optical rotation caused by the upper half will be cancelled out by this lower part of this molecule, okay na. If it is one is dextrorotatory and there will be liborotatory, so one will cancel another, okay. So as a result we will not get any optical activity, okay na. So that's why these compounds are called meso compounds, okay na. What are meso compounds? These meso compounds, in spite of the presence of these chiral carbon atoms, they are optically inactive, okay na, because of the plane of symmetry, and such molecules are called such compounds are called meso compounds, okay. So now the last topic that we are left with is racemic mixture, okay na. Last one is racemic mixture. Last topic that we are left with is racemic mixture. Racemic mixture. Last one is racemic mixture. Now what is racemic mixture? Racemic mixture means the enantiomer of any compound which has equal amount of this D and L isomer, okay na. Suppose if you consider this glyceraldehyde, it may have this plus isomer, it may have this minus isomer, okay na. So it may, this plus we can indicate as D, this one is L. D means dextrorotatory and L means liborotatory, okay na. Now if the isomer of any compound, or if the enantiomer of any compound has equal amount of this D and L isomer, suppose the percentage of this D is 50% and the percentage of this L is 50%, okay na. If they have the equal amount of this D and L isomer, then such a mixture is called racemic mixture. Such a mixture is called racemic mixture, okay na. So if the enantiomer of any compound has equal amount of this D and L form, then this is called racemic mixture. And this racemic mixture are optically inactive. Optically inactive because of internal composition, means the optical rotation caused by this part will be exactly cancelled out by this L part, okay na. So one rotation will be cancelled out by another part, okay. This racemic mixtures are optically inactive, okay. And the process by which this dextrorotatory or minus isomer, okay, enantiomer, the process by which any of these plus or minus isomers that are converted into racemic mixture is called racemization. Okay na. If you take this any plus isomer, okay, and if you convert this plus isomer into a into a racemic mixture, then this process is called racemization. Okay na. So the conversion of any enantiomer, either plus or minus, into racemic mixture is called racemization. Okay. And what is this racemic mixture? Racemic mixture means the enantiomer of any compound which contains an exactly equal amount of this D isomer and L isomer, and they are called racemic mixture, and these racemic mixtures are optically inactive. Okay. So for today's class, up to this, in our today's class, what we have discussed? We have discussed about the optical activity. First of all, we have discussed about plane polarized light. What we have discussed? This plane polarized light means the light, this ordinary light, after passing through this nickel prism, it will have a vibration only in one plane. Such light is called plane polarized light. Okay. And after that, we have discussed about optical activity. Optical activity means any organic compounds, okay, now, which can rotate the plane polarized light, they are called optically active substance. Now if this compound rotates the this plane polarized light in the right direction, then this will be called dextrorotatory. and if it rotates in the left direction, then it will be called as levorotatory. After that, we have discussed about asymmetric molecule. Asymmetric molecule means any molecule which lacks all types of symmetry, then this is called asymmetric molecule. After that, we have discussed about chirality. Chirality means any object which forms a non-superimposable mirror image. Non-superimposable mirror image, they are called chiral. They are called chiral, and this phenomenon is called chirality. This phenomenon is called chirality. Okay. And after that, we have discussed about enantiomer. Enantiomer means any optical isomers which form non-superimposable mirror image. Non-superimposable mirror image. Okay, they are called enantiomer. We have considered the example of glyceraldehyde. Okay, na. So this is the example of enantiomer. After that, we have discussed about diastereomer. Diastereomer means they are neither superimposable nor they form mirror image. So they are diastereomers. Okay. So with the help of this 3-bromo-2-butanol, we have seen the example. We have discussed this diastereomer. And after that, we have discussed about mesocompounds. These mesocompounds, what are these mesocompounds? These mesocompounds means these compounds, in spite of the presence of these chiral carbon atoms, okay, they does not show any optical activity. Okay, na? So such type of compounds are called mesocompounds. And we have seen that in this mesocompound there is some plane of symmetry, and because of this plane of symmetry, there is some internal compensation. Means the optical rotation caused by the upper half of the molecule will be exactly cancelled by the lower half. Okay, so as a result, we will not see any result in optical activity. So that's why they are optically inactive. And lastly, we have seen that racemic mixture. Racemic mixture means the mixture of two optical isomers, okay, which is exactly equal amount of D and L form. D and L form, they are called racemic mixture, and these racemic mixtures are also optically inactive. Okay, so with this we are going to complete our this chapter, this haloalkanes and haloarenes. We have discussed all the topics thoroughly. Okay, na? So thank you everyone. Okay, na? And after a few days, we'll come up with I'll be coming up with a new chapter, and we'll meet again. Okay, thank you everyone.